operations per second, what it affects in our day-to-day life, and how it is being developed and the challenges associated. Okay? Any questions, comments? Feel free. Let this session not be only one way.
In this 15.8 trillion operations, are the switching activities of the transistors or logic operations?
It is the switching activities.
So what is the mechanism to measure it?
In terms of normal i7 processor and this one, when you compare that processor with this one, in terms of performance, whether operation that can do, this also can do.
Let me give you a lateral thinking instead of giving a yes or no. Any market is very specific for any particular product. There is nothing which solves all the purposes. The example for this is this particular processor which we are talking about being powerful and things. The very best part of it is it's not as power heavy as the i7s and the i9s are, because the application is different. This guy runs only for 3 hours, after that it dies. If this also runs for 3 hours and dies, you wouldn't take it. Right? So is it powerful enough to compete with the Intel processors, which are the desktop or the server processor? The answer is no. And let's see what actually we can get it realized. Okay. So from a physical design perspective, I think one thing that we all should understand, that this is a way. Am I audible without this?
Yes, sir, you are audible.
Can you turn it off because it's making this sound?
You are audible.
No, it's making this sound, so.
No.
Okay, that's fine. So, physical design is something that it realizes the logic. You may have a logic in your mind, but unless and until it gets realized, it's as good as planned, which is not being executed. Okay, so that's where we will get into it, that how it helps us and what helps it to realize it. Okay, we have a set agenda, but we don't need to go through everything in the agenda as such. I would like this session to be as interactive as possible. Feel free to stop, ask questions, anything at any point of time. We don't have to be very formal with this, so feel free. And I think with that, we'll just touch a little bit about the agenda. So we'll look at the industry and the trends, as I said. The foundries, which enables the technology, and then the EDA department, which enables or gives us the tools to help us to develop, design and verify it. Then we will get into the physical design, which is normally called as RTL to GVS flow. We'll look at the overview of it, where we fit in the overall design cycle.
So at the SoC again, we have all these test bench components hooked up, right? And mind you, these are, I've just given 3 boxes, but if you see the complexity of the test bench at the SoC, it is humongous, okay? And I couldn't fit it into a slide literally, right? So there will be, multiple VIPs, there will be a processor element, there will be, multiple JTAG interfaces or JTAG BFMs that you want to, use in the SoC environment, right? So this is the, high level how the SoC environment looks like, right? Of course, it's at a 30,000 feet level, so it's very simplified, but this is how it is. Okay? So at the SoC, what do we primarily focus on, right? Now we have verified the IP, we have verified the subsystems, right? So all these are now integrated into the SoC. Now, in addition to that, there will be many. There might be a glue logic in the SoC that is not verified anywhere else. It might just be verified at the SoC level. There might be an IP, for example, your PLLs or your GPIOs or things like that, right? Peripherals, right? Which form the SoC infrastructure, and they are verified as a part of the SoC verification, right? Of course, PLL might be verified at the IP level, but how you use the PLL will be verified at the SoC level only, right? So in your SoC level, we do, it's primarily pre-verified IPs and subsystems. Then we do a lot of black box verification. Now, what do you mean by black box? Earlier, I was mentioning about white box, where you probe into the IPs, and you know that at the SoC, it is not easy to probe into an SoC because there are so many interfaces. Because IPs might come from a third party, they will not even expose the IP to you. You are just exposed to the interface of the IP, right? So for that, we do a black box verification. Now, at the black box level, like we consider the whole SoC or a part of the SoC as a black box, like we don't know what is inside, right? We assume that that part of the black box is verified. For example, an IP which has come to us, it's completely verified. So we assume that IP is verified, we don't need to do anything apart from using the IP at the SoC. How do we use it? Its application at the SoC. That is what we need to test, right? And then, as I mentioned, the verification IPs at the SoC, there will be, firmware. So this is a very important part of SoC verification. As Sanjay was mentioning, you have the software as an integral part of the SoC. Essentially, that is what drives the SoC, right? Now, this firmware is something that is loaded into the CPU. There are various mechanisms of doing that. And then the CPU starts up and executes the code, right? And I'll show you how it is. There is a diagram for this. And then we have both firmware and UVM is the universal verification methodology. These sequences, how are they used, right? So these are all used at the SoC. Of course, I mean UVM sequences are used at the IP subsystem and SoC, but firmware and UVM together as a as a combination of two different methodologies are used at the SoC only. Okay? Because firmware subsystems and IPs don't have a firmware requirement as such. Right? Okay. So to your question, directed and random thing, right? So now, what do we test at SoC essentially, right? If you see the list of test cases here, right? We have, I mean, these are the broad categories at SoCs, right? We have something called as a directed test. It's not to say that they are not used at the IP and subsystem. They are also used, okay? But it's, of course, there is a overlap between IP subsystem and SoC, but these are some specific things that we do only at the SoC. For example, if you talk about, say debug interfaces, they will not happen at, they usually don't appear at the IP or subsystem, right? They come only at the SoC level. Then you have, performance testing, for example. There are, I mean, of course, as I said, there is an overlap between IPs and SoCs. There are certain things that make sense, only at the SoC level. For example, there is so much of integration which is happening at the SoC. So connectivity is a big challenge, right? So we don't know what IPs are getting connected, how are they connected, are they connected with the right clocks, are they connected in the right power domains, right? All of that is very critical in the SoC testing. So we have debug interfaces, we have interrupt testing, performance testing, connectivity testing, security testing, right? So these are mostly directed because, for example, for an interrupt testing, you know exactly what error will generate what interrupt at the SoC. So we can directly go and inject that error at the SoC, and then we see that, okay, at the GPIO pin or at a register, is that interrupt getting registered or not, right? So that is directed, very specific, right? Then we have constraint random. So when you say random testing, right, there is, theoretically speaking, you can call it random, but practically there is nothing as completely random. You cannot have something which is completely random. It is always constrained random, right? Because if it's random, the scope of verification, it just magnifies. You don't know what is random, right? But if you constrain it within a limit, because you understand that, hey, this SoC can only operate with certain power voltages, it can only operate with a certain data path width, or it can only operate with a certain power domain, then you can constrain it, right? So, sorry. Okay. So you have data path, which is mostly the SoC flow. For example, for any SoC, as Sanjay was mentioning, you have the memory, subsystem. So the CPU can come read from the memory. It can put through the DMA. It can put it into some, place, and then the PCI, some device can come and read from that. So that is a data path, right? Then there will be certain control path testing. right? Where you have back pressure, where you have different other protocols which get validated in the control path. You have a register access at SOC. Of course, there are thousands of registers. So, and each IP has its own set of registers, right? So all of that is used in the constraint random. Why I put it under constraint random is if you have thousands of registers, because certain things are already verified at the IP or subsystem level. So you don't need to verify each and every bit of each and every register at the SOC, right? You need to know what your SOC's application is, and depending on that you verify the registers, okay? Then you have the peripheral tests like SPI, UART, GPIO, which are the peripherals which talks to your external VIP or the verification IP agents, as I showed you in the last slide, right? The third category is extremely important, which is called the use case testing. Now, this happens only at the SOC, right? Why? Because when a customer takes an SOC, he or she knows what are the use cases of that SOC. He might not run that SOC at all applicable modes, right? He might choose that, okay, fine, I will just take the, as you said, like audio part of this SOC. I need only that, I don't need the other part of it. So depending on the customer need, we go and run these use case tests depending on what they have, right? Of course, we have to verify everything since we're delivering the SOC, but we prioritize, these kind of testing at the SOC level, right? So there is running the ARM Cortex. So this is nothing but the processor, right? With the actual firmware that happens at the SOC. Then we have concurrent testing from multiple sources, right? So what we have is basically at the SOC, if you see there are multiple inputs coming in from different IPs or subsystems or whatever. So you have this kind of a concurrent testing. Then we have like, so then we have these use cases defined by the architecture or team, which is again driven by the customer requirement, of course, right? So these are the very high level test case categories that we run at the SOC level. Okay. So any questions so far on this? Okay. So now then in SOC verification, we have certain platforms which which we run on, right? So of course it might not be the same team doing it. There might be different teams doing different levels of verification. But what we essentially have is IP level, subsystem level, simulation, or the top level or the SOC level, whatever you call it. So these three I've already discussed, right? So something that comes up is called the GLS, right? Now, what is GLS? It is gate level simulation, right? When we have an SOC or an IP, when you synthesize it, it gives you a netlist. Right? Netlist is nothing but a set of gates connected to each other, right? Now, from an RTL logic, which is in, you have a code, you convert it to a netlist. So that netlist verification is something that we have and which we call it as a gate level simulation. Okay. Now, why do we do this? Is to uncover critical timing issues and constraints, because this timing issues and constraints cannot be covered by the usual functional simulation flows. Okay, that's why we do this, right? The challenge with the gate level is it has a very large runtime. It is extremely difficult to debug because it is all netlist. There is no code there, right? You just have wires connecting to each other, and it's very difficult to debug. Okay, and you have very limited visibility, right? And these simulations, in general, they take a long time to run, especially at the SOC level, because SOC simulations by themselves are very slow. Right? A simulation can easily take about, if it's a very, intense simulation, it will take about 2 to 3 days to run one simulation, right? Now, when you have gate level simulations, it might take a week or something to run. Now, imagine you are running a simulation, and after a week, you come to know that it has failed because of some, stupid error that you have made. So those kind of things are a problem. So when you do this kind of a gate level simulation, you must be very sure to know what you are running. Otherwise, you just lose out on time, right? So that's difficult.